Hello everybody and welcome to this seminar on the IS 10101 5th edition of the regulations and the changes as they relate to surge protection and in particular relating to panel builders. So just as an overview, we're looking at the new standard. This also applies to the 18th edition of BS 7671 wiring regulations about the selection and erection of surge protection devices. Now, both standards are primarily written for the designer and installer, but the panel builder needs to have knowledge of section 534 and SPDs so that the panel that's being designed and the board layout meets the requirements for providing the best possible protection levels by having the lowest let-through value or UP levels. So we'll have a look at that now. In section 443, there is this table, the rated impulse voltage, and this is the protection level that we need to meet with our SPD. So what we can see across the top are the categories of equipment, starting at the origin with the electric meter at category 4, and that's rated at 6 kV. The fixed wiring installation and distribution boards are rated at 4 kV. We're interested in protecting appliances, equipment, tools, stuff like that. And that is rated at 2.5 kV. So the whole point of the SPD is to make sure that the installation doesn't see anything higher than 2.5 kV, otherwise things are going to go bang. And then there is a more sensitive area, which is category 1 equipment, which is for servers, fire alarm panels, any really sensitive equipment. So what we're going to be looking at are ways in which we can make sure that the installation always has a protection level lower than 2.5 kV, so everything's going to be operating okay. In the regulations, there is, in addition to the normal protection level, an argument for having a lower protection level or a safety margin of 80% of the required impulse voltage. So be looking at that table and aiming for approximately 2 kV for the Cat 2 equipment. But you don't have to do that if you have a protection scheme, and I've highlighted this in bold and underlined to figure 534.9, and we'll have a look at that in a minute. And we also don't have to consider this safety margin where there is a volt drop across the overcurrent protection in the SPD circuit is already been taken into account. And this would apply to an SPD which has got a built-in fuse, and we're going to see what the advantage of that is for the panel builder in order to meet these requirements. So to look at this first requirement, the safety margin of only 80%, we'll have a look at this diagram here that was mentioned. That's at figure 534.9. And it shows us that if we were to wire in a V connection, which sort of makes it a series connection, then we do not have to take into account the connections into the top of the SPD. We only need to be mindful of the connection labeled here as item 3, and that's a connection from the SPD to the MET or the main earth bar or the chassis. That's the only dimension we're interested in. And be aware that because the terminals of the SPD are going to be part of the series connection, that their maximum nominal rating needs to be taken into account. So what we have within the product range is the Stack 25. And this will snap into the top of, say, the Type 2s or the DEHN Shield Type 1 devices. And it provides an additional terminal so you can utilize this V connection, bearing in mind the maximum of the 100 amps. So we only really would see this in subboards or consume units. So if you had a dwelling where you had some tails and the only way you could do it was to isolate, just cut the tails, you can stuff both ends of those tails into the terminals, and that can all happen in one slice of the SPD. So here we can see where one terminal is accommodating the first part of the tails, and then the additional terminal, the Stack 25, accommodates the other half, and it's tightened to the correct torque there. The other way that we can reduce the voltage protection level, or the way which is certainly applicable in panel builder design, is the use of SPDs which have built-in overcurrent protection. In other words, an integrated backup fuse. Now we have some SPDs which have a component inside them which removes the need for having any overcurrent protection in the circuit surrounding the SPD itself. This technology is known as ACI, or automatic circuit interruption. When we look at the wiring diagram, if we look at the phase plugs L1, L2 and L3, what we have starting at the bottom of that arrangement is the rectangular shape with the line diagonally across it, and that's the MOV itself. That's the surge protection component. The square above it is indicating the thermal disconnection feature linked to the remote changeover contact you can see there on positions 12, 11 and 14. So when we get to the point where the surge device has had enough, it'll be this part which changes the window from green to red and disconnects the SPD in normal circumstances. But what if part of that circuit became a short circuit? So there was an internal fault and then we have a high fault current. Under these circumstances, it is the upper component, the spark gap, which guarantees that there would be no nuisance tripping and no such fault flowing. Therefore, because of the fact that it is a spark gap and there is no continuity anyway, there is no need for the fuse external in this circuit. And fusing and type 2 SPDs has always been a bit of a problem, and certainly more so with a type 1, because you need it to be small enough to fit in the distribution board and small enough in capacity to pass your short circuit requirements in 61643-11, but you want it to also be big enough to carry the maximum rated impulse values as stated by the SPD manufacturer. Then there's going to be often many compromises made. So whatever we can do as a manufacturer to help with the simplicity of fuse selection has got to be a good thing. So as I mentioned, there is no need for a fuse with this new technology. So that means that we've already done the dimensioning of the overcurrent protection device, i.e. none is needed. The TOV withstand is very much better. That's temporary overvoltage, and that's for, I guess, primarily loss of neutral events, for which the SPD is expected to survive, not necessarily to do anything about it. It means that we can have a small disconnection facility integral to the SPD and correspondingly a very low let-through energy. Because of the spark gap, there's also no leakage current, which could say give false tripping on an RCD, and it also means that you don't have to disconnect this module up to 500 volts when you do your IR testing, because on some SPDs you would have to remove the component or you're going to get a false reading. That's not necessary with this device because again of that disconnection or spark gap element. So there's many reasons why you'd want to fit it, but the removal of the fusing is probably one of the more important for a panel builder. So looking at the evolution of the SPD over the years, so on the left hand side we have a traditional type 2 SPD. This has got 125 amp backup fuses, which is perfectly dimensioned for the SPD, but we're requiring 16 amp cables. Then we got to an SPD with integrated interruption. That was the DEHN CI in the middle there. So the fusing disappears because it's now built in, but we still needed 16mm cable. Now with ACI, the new technology, we can still have no overcurrent protection required in the surge circuit. And now, because of the spark gap technology and no fault flowing through this circuit, we can drop the cable size down to 6mm square. So that means obviously a smaller loom, tighter bend radiuses and lower cost. So in summary, the UP or voltage protection level is one of the most important aspects of the SPD installation. So it's not enough for a manufacturer of SPDs to declare a very low UP level in their data sheets. because it's always going to be the quality of the overall installation, the cable length, the cable size, the addition of an OCPD into the circuit. You add up the volt drop of all of those to get your overall UP level, and all of these components have got to be less than 2.5 kV, and this will be a point which we'll come to in another section in this seminar. We're now going to have a look at the currents that an SPD has to deal with. So looking at the first currents, that's going to be the surge current, INSPD, and this is the value in Ka that this type 2 device has to divert to earth. And it's quite a low bar, it's 5,000 amps per pole, and in the TT circuits the neutral would have to be able to take its own value and that of the output of the phase device, hence why on the CT2 connection method for TT you see that the N to PE plug will have to take either twice its capacity or 4 times its capacity. So looking at the plug from a typical type 2, on the label here we can see that its IN is 20 Ka, so that's easily more than the standard requires. Its maximum is 40 Ka. It's got a low let-through voltage or UP of 1.25 kV, and bearing in mind the maximum allowed is 2.5, that gives you another 1.25 kV to play around with in volt drop. The fuse rating is 125 amps, and we can see the little square there with T2 in it, which is denoting that it is a type 2 device. For type 1s it's a bit different. We don't have IN, we have IIMP, because this is to do with lightning impulse discharge current. And the standard here requires a value of 12,500 amps. And you might think, well, that's lower than the 20 Ka that we've just seen. But this is to a different wave shape. This is 10/350, which is a far more onerous wave shape than the 8/20 of the type 2 devices. So here, looking at a typical type 1 device, this is single phase. We see on the label that it is rated at 12.5 Ka, which is good, at 10/350, and also 12.5 Ka 8/20, or the type 2 waveform. The fuse rating is 160 amps, so if you've got a 150 amp board, you don't need to have an overcurrent device. If you've got a 250 amp board, you will need to have an OCPD. And also visible there is the 1.5 kV let through. So again, very low let through value there. Now that is only typically used in levels 3 and 4. You can see the note under the table there, lightning protection levels 3 and 4. For lightning protection levels 1 and 2, which are the most onerous, you've got to go for something which is rated at 25 Ka per pole. And this isn't mentioned in 7671 or 10101 because this is normally the remit of the lightning protection contractor once they've established the lightning protection level as being level 1 or 2 through the 62305 risk assessment. On the label here we got 25 Ka per pole, a low let-through value of 1.5 kV, and fusing is rated at 315 amps. So that's something to bear in mind when we go on to the next section about fuse ratings. So bear in mind everything we've just been talking about on the fuse rating. It is a requirement of the standards that we need to consider not just the SPD, but the whole SPDA, or surge protection device assembly. So in that circuit from A to B, if I've got a type 1 device rated at 12.5 or 25 Ka, then the overcurrent protection device must be able to withstand that. So you cannot protect a type 1 device with just a simple little 6 or 10 Ka rated MCB. It's going to have to be the fuse as designated by the manufacturer because of its rupture capacity being so much higher, or a molded case breaker rated obviously at a minimum of 12.5 or 25 Ka. So the whole assembly will be rated at the same, so the SPD can't be devalued or derated by using smaller MCBs. That is not permitted under the standard. So in general, looking at the overcurrent protection measures for an SPD, they can be internal to the SPD or external to it and be of the highest value to ensure that the complete assembly meets the ratings, but not so big but it's exceeding the values rated in the manufacturer's instructions. So it's a bit of a balancing act. So that's why we've taken the trouble of having SPDs with the integrated protection, removing you from all the problems with overcurrent protection selection. So looking at a type 1 device, this one, it'll be rated at a minimum of 12.5 or 25 Ka. And normally in our data sheets, we mention GL or GG fuses. So looking at the 12.5 Ka, if you remember the label, that was rated at 160 amps. So the fuse rating, that starts to melt at 20 Ka. So that's perfect for the 12.5 Ka value of the SPD. And on the 25 Ka value, we were mentioning a value of 315 amps. So that is more than enough for the actual value of the 25 Ka, so we're not derating that surge circuit at all. Now, there's absolutely no problem popping in a 20 amp fuse. I mean, the SPD is in circuit, it's obviously connected to the phase bar through the fuse, but when it comes to first surge, the 20 amp fuse is going to pop at 1.7 Ka out of a theoretical 25 Ka that's going to be required. So it's just going to isolate the SPD before it's had any possibility of doing everything that's expected of it. So here's an example of a type 1-2 device with a built-in fuse. Now this is a single phase module. You just select 4 modules for 3 phase. The fuse is built into the device and the voltage protection level or UP level is still less than 1.5 kV. So that more than ticks the box in terms of the requirements of the standard. It'll take 25 Ka of lightning current, so that means it's suitable for all lightning protection levels, and it meets the requirements of both the standards. So it's a very good product if you're looking to integrate the fuse in and have all the problems associated with dimensioning of the overcurrent protection device. They simply all disappear now. You probably still want to fit an isolator in there so you can at least disconnect them for testing or maintenance or anything like that. So according to the standard, we need to keep these cables as short and as straight as possible and to avoid loops. And there are 3 possible cables, A, B and C. But if you go for the integrated overcurrent protection device, cable B is removed altogether, along with, of course, the OCPD. So that gives you a bit more flexibility. And you need that flexibility because the regulations say you cannot have more than half a meter, 500 millimeter of cable length. And if it helps, you don't have to take the earth cable, the PE cable, to the main earth terminal. You can take it to the chassis of the consume unit or distribution board. That's known as an intermediate earthing terminal. That's perfectly acceptable. But what we must do is keep these cables as short as possible. That's why if we can reduce the length of the phase conductors by using inbuilt fusing, it gives you a little more flexibility with the PE connector on the other side. So here are some examples. So we've got an SPD here which is in the board. That's fine, nothing wrong with that. We've got another one which is just underneath the board in an external enclosure. So the cable lengths again are well within specification. And then finally down the bottom there we've got a type 1 device coming out of the main incomer. It's mounted on its side. If that's perfectly okay, if that shortens the cable run and keeps the cables as short as possible. And you can see it's very much adjacent to the MET there. So those installations are exactly what we'd be looking for. The standard will emphasize this point in the appendix where we have the wiring diagrams. And if we look here, we have in the key item number 4, the earthing connection of the SPD, either 4A to the MET or 4B to the chassis, whichever is the shorter route. Only by doing this can you guarantee that you will have the best possible performance in the surge circuit. And this stresses another point in the regulations, that 1 meter of rectilinear cable carrying a discharge current of 10 Ka adds a volt drop of 1000 volts. So if I already have 1.5 kV in my SPD and I have 1 meter of cable, I am at my maximum value of 2.5 kV. And if I can't do this, if I can't keep it below 0.5 meter, then as it says, I need to have another SPD close to the equipment to be protected to make sure that the impulse value of that equipment is not exceeded. How not to fit them? That's good to know. So in this motor control center, we have the main isolator, we've got the fusing, which is appropriate, it's 315 amps, and we've got the type 1, 2 SPD there. But see, the cables are far too long. They sweep from the isolator up to the fuse. Also, there's quite a big bend there up to the SPD itself. And there's a very long earth cable. I don't know why that is. It's a metal box. Just take it to the chassis. So if the whole assembly was dropped down and the SPD was inverted, that would have made a dramatic difference to the cable lengths and, of course, the ultimate UP value of all the volt drops across all of these components. As it is, it's going to be in excess of 4 kV, which means any sensitive electronics within the cabinet and downstream will still likely be destroyed because the value of 2.5 kV has been exceeded. So that cabinet and several others like it were rejected on site, and the panel builder had to go away and re-engineer this. So we can see now the SPD is in a different location. It's in another separate compartment with, this time, not fusing but a molded case breaker rated at 25 Ka. So that's absolutely fine. The cables are much shorter, and they've written on there the note that they did all of this from the phase bar to the earth connection in 630 millimeters, well within the meter. So we've got short cables, low volt drops, and that is a far better installation than what they had done previously. So that's it. Good to end on a high note. If you've got any questions, by all means drop me a line or give me a call, or alternatively have a chat with one of the local domain guys and they can answer your question, or they will may even refer you on to me. But that's it. Thank you very much. Thanks for watching and listening.